Thank you very much.
Thank you. Yeah, glad to be presenting here. Yeah, so we're comfortable with this. Let's see. Yeah, okay. Great. Yeah, glad to be presenting here, and this is a joint work with Javier, Marcello, Manfred, and Paul. Javier and Paul are already present here. There is a slight difference in the title because we had some nice, exciting developments of the past few months, but I can promise to not be completely unfaithful to the advertised abstract. Basically, we will be seeing latent variable estimation using derivative Gaussian processes and then some approximation strategies. So this derivative Gaussian process latent variable model was something that we developed during my PhD, and essentially what it is take Gaussian processes, then there are these extensions, namely derivative GPs, multi-output GPs, and latent variable GPs. We do an ensemble, get one model, and the purpose of this model is to accurately estimate latent variables, and the other two extensions simply assist in doing so. In the next few slides, I will simply explain, very quickly explain these three extensions before moving on to approximation strategies. So derivative GPs, it's basically you take GPs f with the chosen covariance function, and you can get a derivative process, let's call it f1, which will have a derivative covariance function in the squared sense. You can then model both of them together jointly, and then you're just working with this a little bit more elaborate covariance structure where you have the chosen covariance function k, its partial first order derivatives in the off diagonals, and then the second order partial derivative. For multi-output GPs, it is basically we are looking to estimate, we are looking to analyze matrix variate responses instead of the more traditional column vector responses. So what we do is we first specify dimension-specific individual GPs, which means it has dimension-specific covariance functions and their parameters, and then we use the Cholesky factor of between output correlation, multiply it to our individual GPs to obtain correlated, across dimension correlated Gaussian processes. Yeah. Well, of course, we also basically do the same thing with the derivative quantities, so it's the same treatment. Then we move on to specifying our outputs and the derivatives conditioned upon f and f1, respectively. And at this stage, we also introduce this intercept term to account for any mean shifts. Of course, our objective being latent variable estimation, we can try to estimate the latent variables at this stage, but we will inevitably run into identifiability issues. What we do is we take a measured quantity, let's say x tilde, and assume that it is like a noisy variation centered around the true latent inputs x with some measurement standard deviation s. Of course, all of this was exact Gaussian process, which means we have this computational issue where it scales cubically with the sample size. So we need to address that. But because we take care to get trustworthy latent variable estimates, we only approximate the covariance function, still keep using MCMC for inference. To approximate the covariance function, we choose Hilbert space approximations. So for those who are not aware, I will do a very quick overview of what HSGPs are. We simply work with these four elements, let's say. So we start with a stationary covariance function. We obtain its spectral density. And based on a Dirichlet boundary condition on the input space, we can get a closed form eigenvalues and eigenfunctions. Using these four elements, we can express the covariance function as an infinite sum with these elements, and then we can approximate that using a finite number of basis functions m. what happens in the covariance matrix space, so it translates to basically saying, okay, we have a covariance matrix, and then it can be approximated using its eigenvalue decomposition, which has this phi matrix, which is simply a matrix of the eigenfunctions. And then there is this diagonal matrix delta with the spectral density and eigenvalues. Then we can specify our GPs, replace the covariance matrix, and then it yields this linearized form of the GPs, where we can then see it can scale linearly with respect to the basis functions and the sample size. Now we would like to extend this to our derivative GPs. So we are again working with this more elaborate covariance structure. Our initial idea was to attack the quadrants by using some block-wise HSGP approximation, so a block-wise low-rank, reduced-rank approximation. And what happens is that, of course, it is fairly easy to obtain the HSGPs of K and K11 because they're covariance functions. Not so easy when it comes to the off-diagonals. So to illustrate that, let's take the first-order partial derivative of the squared exponential, and we see this highlighted term. What happens is that this term renders the expression antisymmetric, which means we will not get any real spectral densities. One option is that we completely drop the terms, and we just work with K and K tilde. K11. Let's call this partial derivative HSGP. Another more general form is that we are simply using the same structure, but these are two different processes that has their own covariance functions. Let's call it partial composite HSGPs. These were basically the models from the submitted abstract, but now we can use them as reference models. To get the full derivative HSGPs, what we needed is to think about derivative of HSGPs instead of HSGP of derivatives, which we were doing. What that means is that I can illustrate using this eigenvalue decomposition form, where we can now express the joint derivative structure, where we start with the eigenvalue decomposition of the correlation matrix, and then let the derivative operator act on the eigenfunctions instead of the spectral densities, which means that the spectral density actually remains same as opposed to the previous method. Only the eigenfunctions change from phi to, let's say, phi1, corresponding to f1. Then we simply write down the linearized version of the derivative step, which is f1 now, instead of using phi, only has phi1. And all of our models are implemented in Stan. And in Stan, essentially, we simply need to code these two key steps. And why? Because once we do that, then the joint structure is actually implied, which means you can just take the covariance of f and f1 and you get the cross covariances back. So you don't necessarily need to code them in your Stan code. Now, there are some practicalities that we need to take care of when it comes to working with HSGPs, which means we need to determine the number of basis functions. We need to determine a constant that adjusts the scale of the inputs so that we can take care of the boundary conditions. These two things need to be set based on the smoothness of the functions, which means for, let's say, a Matern class of covariance functions, after choosing the covariance function, we simply need to take care of the prior on the length scale and see what we can do with M and C. So we do some sensitivity analysis, which means we just generate huge K11 matrices and K10 matrices, compare it to their eigenvalue decomposed form. And what we can see here, as an example, is, let's say, for an x, for an input in the range of 0 and 1, if we set rho to be 0.1, we need a C of 1.5 and M to be somewhere around 25 to have a good enough approximation. Of course, for all the other cases, we need to just see what happens, and then we check. Then we move on to some simulation studies where we check how well our model recovers the latent variables. To do that, we do some setup where we generate 50 simulated data from the ground truth, which is our exact derivative Gaussian process, which we started with. And then we compare the posterior samples from that to our with the posterior samples of the latent inputs of our proposed model, derivative HSGP. Of course, as I promised, the partial models, both the exact and the approximate forms, they are in the reference. And then we additionally also use some single data source models, which basically means if you modeled y and its derivatives separately. This emphasizes, or at least helps justify, the joint covariance structure that we're dealing with. So what we see is that we actually get the same level of accuracy with our approximate models, the HSGP, which is our proposed model, when compared to the ground truth. Quite expectedly, we do massive improvements over the partial models, where of course the partial models leave out so much information. So essentially, we now have a full derivative approximation that can be fast and can be applied in different scenarios. Additionally, we also see a steady decline in the accuracy, so like decline in RMSE when we increase the number of output dimensions, which is nice when you have data scenarios where you have more output dimensions. For a larger sample size, so n equals 200, we leave out the exact models but fit all the HSGPs. And here we also introduce the single data source models. And here we, of course, again see that our derivative HSGPs has an edge over the partial models, again, expectedly. And of course, we also have a very sharp increase in accuracy when compared to the single data source models. We still retain the steady decline of RMSE when dimension increases. And yeah, the data in this, the data generating process is still the derivative Gaussian process, the exact one. Okay, so to summarize, we developed this general method that accurately estimates latent variables when you have access to derivative information. We do we can use this in complicated data scenarios where you have, let's say, matrix varied responses, and you would like to have continuous latent variable estimation. One specific application that motivated our exact derivative paper was estimating latent cellular ordering based on gene expression data in a single cell level. Basically, by doing so, and there we had access to derivative information that comes from difference in splicing dynamics. And by doing so, we simply provide posteriors that might help understand the underlying biological process better than, let's say, if we had modeled gene expression separately. Yeah, of course, there are lots of open problems that come with this method. For example, even nice applied problems that I have not investigated. So if any of you have nice applications, I would be more than happy to talk about that, like for the remainder of the conference, or you can, of course, contact me over email, and for my other works, you can check out my website. Yeah, thank you.
Having my own mic issues. Okie dokie. Are there any questions from the audience? There's one on the left-hand side over there.
So, I wasn't clear why you were calculating derivatives. What are the derivatives for in this?
So as I said, it starts with this application motivation, which I actually omitted. So I can basically do this, where we have these single cell data, and then we have access to a derivative information which comes from a splicing dynamics of, so you have unspliced data, you have spliced data, the rate of change of splicing can be considered as a derivative information to the spliced data. And essentially what we want is to estimate the cellular ordering, a continuous temporal ordering, which is not there because of the technology that is being used to collect these data. So essentially that's a latent variable. And this directional information helps us to better estimate the cellular ordering.
And you're doing it jointly with the actual GP and the derivative GP because you care about discovering the original GP given the observation of the derivatives?
No,
is that what this is saying?
No, we're still using both the GPs only to estimate the latent variables. So we're not computing the GPs back. So both exist, we model them, and conditioned upon that we estimate the latent orderings. That's it.
Thanks.
Can I just quickly ask, is this kind of like similar to something like RNA velocity modeling in this sort of context?
Yeah, exactly. So we are using RNA velocity as the derivative quantity.
Okay.
Yeah. So.
Yeah, no, it makes a lot of sense. And could it be used, I guess, in other applications where how are you validating it actually as well in this kind of context?
Yeah, that's a good question. So essentially we have these quite large simulation studies where we actually see our models are recovering quite well enough. Of course, we actually haven't focused too much on the application point of view so much, but I mean, I can show something. For example, this. So there was this data set that we were trying to analyze and cluster computing. Mm-hmm. So this result just came in this morning, where we can basically see that there are some prior times, which is the X tilde, and then based on that and the gene expression data, we can get these continuous posterior latent X's. We hope that this continuous temporal ordering would help us understand the interaction between the states better than the priors. So, and the priors are basically measurement time when the data was collected.
Yeah, no, totally makes sense.
So, yeah.
In this context, sorry, I'm looking around to see if anyone else has questions. In this context, would you be able to do the same sort of things if you potentially had like bifurcating behavior? So you have this two different axes at the same time?
That's a plan that's in my to-do list.
Sorry, shouldn't have asked.
No, that's all good, because the thing is that, of course, now at the moment we are doing a single latent input dimension. Mm-hmm. There can be another latent input dimension which can represent the branching dynamics. Of course, we would have to figure out how. Yeah, and how you actually determine where that takes place seems to be a bit of a... Well, I think the point would be to determine if the branching takes place or not. Yeah, interesting. All right. Yeah. Well, let's thank our speaker once again. That's really great talk. Thank you.